Here we are discussing velocity of sound, longitudinal waves in solids. So sound waves are longitudinal waves in the nature. Longitudinal waves in the nature. In longitudinal waves, particle vibrates parallel to the propagation of the wave. Parallel to the propagation of wave. This longitudinal wave can travel in the form of compressions and rarefactions. The velocity of longitudinal waves in the solids. Let us discuss the velocity of longitudinal waves through solids. So first I am considering about there is a solid, it's a rod, its a cross-sectional area is A. So this is what a rod is taken, is the end O. This is the cross-section. So I'm choosing about a small length element from this. This is a length element. It's what AB. Length element AB distance is dx. Its distance from the point O is what? This is what x, and this one is what? It's a dx. So total distance from the end O is x plus dx. Distance of length element from O, from the point O, is equals to x plus dx. So now, when the particles in the medium are vibrating, let this medium, the sound propagation from left to right. The sound propagation is from left to right, and the particles in the medium are vibrating from their mean position. So here we can say that the wave is propagating with a speed is v. Wave is propagating with a speed. So in this direction, the propagation of wave is observed. So this is what a small cross section is taken. This cross section, in my view, this is what a small length element. In this medium, particles are vibrating along with the propagation of the waves, like this. So the distance from here is what? X. This is x, and this one is what? Dx. Total distance is what? X plus dx. So due to the propagation of the wave, a stress is developed. Means the force on each particle in the medium is developed. So this is each particle, so some force is developed here. The force per cross-sectional area is stress. A stress is developed. So is called what? It's a stress. Now we can talk on this. From stress is equals to force per area. It's a cross-sectional area. This is the, so stress developed in this. And next one, as we consider, then after a time t, after a time t, the propagation, so propagation, it increases from, so from this is what the distance we consider before, the distance is what, here if we choose as from here, this is what small distance is taken, it is after a time t, this become as it vibrates, this is the initial length, just to please observe, it's a initial length. Initial length is what, dx plus dy increased. Initial length is what, dx plus dy increased. The change is occurred. So from this end, this is what, x plus y. So I'm trying to say here, this small length element is taken. The length element is from this length element after a time t, this may vibrate up to here like this, up to here. So this, the change is what you say, it's a dy. So total is what, dx plus dy. So now the strain is, stress is developed along with this. Now strain is developed, okay. So the strain in a section, what is this? This section is what? I'm taking this is A and next one B. The strain developed, strain is developed in section AB. So what is the strain? Change in length per original length. So strain is equals to change in length. What was change? This is the change. It's a dy by dx. dy by dx. So now from Young's modulus, y is equals to stress by strain. Y is equals to stress by strain. What is the stress? F by A. What is the strain? Delta, that's what? dy by dx. So it's a continuation from before page. Y is equals to stress by strain. So it's a stress by strain. Stress we written F by A. Strain is what? dy by dx. From here, F is equals to y A. A is the cross-sectional area which is passing through here. This is dy by dx. So this is the force, so developed in the cross-section AB. So that's what F is equals to ya dy by dx. So next we can talk on this. So what is the force? The net force on cross section, just I'm considering it's a df. Df is equals to dm into a. Df is equals to dm into a. dm is density into cross sectional area and into dx. A is what? Which is making oscillation. So that's what? D square y by dt square. So from df is equals to rho a into dx. Next one, d square y by dt square. So df by dx is equals to rho a d square y by dt square. So next one, from here this is what df by dx is taken as is what? One condition. Okay. So next one, In before equation is what? This is the equation. So just I'm taking about it's a f is equals to ya dy by dx. Differentiating this equation, differentiating with respect to x. So df by dx is equals to, this we are doing, df by dx is equals to ya d square y by dx square. This is one more equation. So this is another equation. So let it be, I'm taking this is 1 and this equation is what it's a 2. So from these two conditions, from the equations 1 and 2, from equations 1 and 2. So df by dx means what? Ya d square y by dx square is equals to rho a d square y by dt square. D square y cancel. A and A cancel. So this is y by rho is equals to a dx square by dt square. Dx by dt is what? Velocity. Velocity v is equals to under root of y by rho is the relation. So y is the Young's modulus, rho is the density of material.